A couple examples of some inverse trig that I want to work with you here, maybe 3 of them. One of the things that comes up, particularly in Calc 2, you're dealing with certain types of stuff. Actually, I guess it comes up in Calc 1 as well. Where trig functions are useful, and so the inverse trig functions become useful as well. You get some expressions that look something like this. I want the sine of the inverse tangent of x over 2. Right? And so this is a lot like the one that was right at the end of the video before, except that rather than having numbers completely, I've got some expressions there, x and 2. But there's a triangle involved here, because this tangent inverse of x over 2 is the angle whose tangent is x over 2. So I can draw a triangle where I want this angle to have tangent x over 2. And I chose those two sides because the tangent is the opposite side divided by the adjacent side. So if I make the x be the opposite side and the 2 be the adjacent side, that ratio of sides is the tangent of this angle. Right? So the tangent of this angle is x over 2. This angle is the arctan of x over 2, or the inverse tan of x over 2. But once I have that, I know the third side. You tell me one trig function, I know them all. Right? So this is the square root of 2 squared, which is 4 plus x squared. So what's the sine of this angle? What's the sine of this angle right here? Well, the sine of that angle is the opposite over the hypotenuse, x over the square root of 4 plus x squared. Okay. Let's try one more like that. How about the tangent of the inverse cosine of x? Now, this looks a little funny just because it doesn't look like a ratio of sides in here. It's just an x. But it's always ratio because you can think of it as x over 1. So I'm saying I have an angle whose cosine is x over 1. I have an angle whose cosine is x over 1, right? Adjacent divided by hypotenuse, it'll be x over 1. This angle right here is the angle whose cosine is x over 1. I want to know the tangent. Well, in order to know the tangent, I got to know the opposite side. But oh my goodness, if you give me one trig function, I know them all because I've got the Pythagorean theorem on my side, right? So if I take this one squared and subtract that one, 1 squared minus x squared, which is just the square root of 1 minus x squared, sorry. I've got all 3 sides. What's the tangent now? The tangent of the inverse cosine of x is the square root of 1 minus x squared over x. One thing I want to warn you about, because there's a really common mistake here, is that people do this. They do this all the time. They look at that square root of 4 plus x squared and they write 2 plus x. And I say, oh, no. The square root of 4 plus x squared is not 2 plus x. The square root of 4 plus x squared is the square root of 4 plus x squared. It doesn't break up because square root doesn't distribute over plus. Likewise here, I see a lot of people look at the square root of 1 minus x squared and say 1 minus x. It's like, oh, no. Try some numbers, plug them in. It doesn't work, right? If x for up here, if x is equal to 2, for instance, 4 plus 2 squared is 8. Square root of 8 is not the same as 2 plus 2. Right? Okay, so it just doesn't work with numbers. You can't do it. Just leave it like that. Leave it like this. Okay. Point is, if I say inverse cosine of something, then I've just told you 2 sides. If you get 2 sides, you get all 3. You can figure out any trig function you want. Okay. There's that kind of example. There's also things like this that I want to do. What is the cosine of the sine inverse of 2/3 plus the tangent inverse of 5/4? Well, this is the cosine of a sum of 2 things. Each of these things is an angle, right? This is the angle whose sine is 2/3. This is the angle whose tangent is 5/4. So this is like a cosine of a plus b, where this is a and this is b. So there's a couple of triangles I need to draw here. I got to draw one with this angle A. And the thing I know about A is the angle whose sine is 2/3. A is the angle whose sine is 2 divided by 3. So this side over here is going to be 9 minus 4. It's the square root of 5. Right? Notice, if I did square root of 9 minus the square root of 4, that would be 3 minus 2, which would be 1. That's not the square root of 5. So you can't split that up. It's just the square root of 5. Likewise, there's another triangle, that's what I want to say, where this angle is B. And what do I know about B? I know that B is the angle whose tangent is 5/4, right? B is the inverse tangent of 5/4. So if I make this 5 and that 4, clearly I didn't draw it to scale because the 5 should be bigger than the 4, but okay. But now I can use Pythagoras to get this other side. This is the square root of 16 plus 25, so that would be the square root of 41. Right? 41. So I know a lot of stuff about A and B, and I want the cosine of A plus B. I've got an identity, right? This is the cosine of A times the cosine of B plus the sine of A times the sine of B. No, it's not. There's a minus sign in between. Good. So, what do I know? A was the angle whose sine is 2/3. So what's the cosine of A? Cosine of A? Well, it's square root of 5/3. B was the angle whose tangent is 5/4. What's the cosine of B? Well, it's 4 over the square root of 41. What's the sine of angle A? Well, A was the angle whose sine is 2/3. What's the sine of A? Well, it's 2/3. What's the sine of angle B? B was the angle whose tangent is 5/4. So the sine is 5 over the square root of 41. So I've never in this thing figured out what angle A and angle B are. I never typed that into my calculator and said, oh, arc sine of 2/3 is whatever the angle is, or I never figured out what this angle. I didn't need to because I knew the sides and I could get the third side. Anyway, this is 5√4 minus 5√4. How about 4√5? Let's try that again. Yeah, 4 times the square root of 5 minus 10 over 3 times the square root of 41. Okay. Cosine of a sum. These are two angles. I know a lot of stuff about those angles because I told you the sine of this one. I told you the tangent of that one. So we got all the information we need. One last one here that I want to do. It's very similar. I want to do the sine of 2 times the inverse sine of 5/13. Now, yeah, you can use your calculator and say, what's the inverse sine of 5/13? But what fun is that? I mean, we can do this without using that inverse trig button on the calculator because I know a lot about this angle. This right here is an angle. It's the angle whose sine is 5/13. Oh my goodness. Here's A. I want the sine to be 5/13, right? And now I'm asking you, what's the sine of twice that angle? Twice that angle. Well, that's going to have to take a little more work. But I've got a double angle formula, right? This is the sine of 2 times A. That's equal to 2 times the sine of A times the cosine of A. Yes, it is. And do I know the sine of A? Heck, I was given the sine of A because they told me that A is the angle whose sine is 5/13. So what's the sine of A? It's 5/13. What's the cosine of A? Well, let's take a look at this triangle. Cosine of A should be this side divided by that. Can I find this side? Of course I can find this side because I've got Pythagoras on my side. Square root of 13 squared minus 5 squared turns out to be the square root of 144, which is 12. So that side is 12. The cosine of A is 12 divided by 13 for a grand total of 120 divided by 169. Yay! Okay. Inverse trig functions. when they give you an inverse trig function of some number, they're telling you I've got an angle, and they're telling you a ratio. They're telling you two sides of a triangle. Man, you got a lot of information from that. Okay, there we go. There's inverse trig. Ask your questions in the homework question discussion. There we go.